The question is, could you do an example on determining the combined stresses? In this example, I'm going to show you how to combine stresses due to the shear force V, the bending moment M, and the torque T. This is the problem that I have chosen here. We have a cylindrical shaft subjected to two things. It is subjected to a torque of 5 kilonewton meter at the end, like shown in this picture. It is also subjected to a force of 10 kilonewton in the direction of y, again like shown in this picture. We are interested in calculating the combined stresses at point D and E on a cross-section that is taken at point A. In a broader sense, these are the steps. First, we want to determine the internal forces at point A. In this particular example, we're going to find there's going to be a shear force V, bending moment M, and a torque T. Step 2, we determine the stresses at point D and E due to each of these internal forces and combine. If you recall, these are the relevant formulas for calculating the stresses. The torque T is going to produce a shear stress that varies linearly with the radius rho, and this is the formula for calculating the stress. The bending moment M produces a normal stress, and this is the bending formula for calculating that. And the shear force V produces a shear stress, and this is the formula for calculating that. The focus of this video is in combining the stresses due to these different kinds of internal forces. My coverage here of the remaining steps is going to be pretty cursory. Let's go through the detailed steps. Step number 1, find the internal forces. I'm going to section the shaft at point A and separate into two parts. Then I'm going to consider the right side for finding the internal forces. So what I have done over here is to mark only the non-zero internal forces. So these are the non-zero internal forces. We have the moment about the z-axis, and we have the torque about the x-axis, and we have a shear force in the vertical direction or in the direction of the y-axis, Vy. And of course over here, the same quantities are going to be acting in the opposite directions. So there are three of them. We need three equilibrium equations to find them, right? So here are the details. I'll let you follow. Step 2, we go ahead and calculate the stresses due to these internal forces. There are a couple of things we need to do before we can do that. First, we need to calculate the relevant geometrical properties. And in this particular case, we need the second moment of inertia about the z-axis, the polar moment of inertia Jx, and the capital Q for point E. This is the formula for the second moment of inertia for a circular shape, and we get a value of 4.911 times 10 to the minus 6 meter to the power of 4 for that. The polar moment of inertia for a circle is twice as much as the second moment of inertia, so that is 9.822 times 10 to the minus 6 meter to the power of 4. Now we need a value for capital Q. What do? We draw a line through the point, and in this particular case it's point E, parallel to the z-axis. So in this case you can see it turns out to be the z-axis, right? Now you use either the top part or the bottom part to calculate this quantity. Here I have chosen the top part. QE then is A prime times Y bar prime. A prime is the area of the shaded part. Y bar prime is the distance to the centroid of that shaded part from the z-axis, right? So the formula for that is 4c over 3 pi, where c is the radius of the circle. Now you can easily follow this. You get a value of 83.33 times 10 to the minus 6 meter to the power of 3 for QE. The corresponding value for point D is 0, and that is why the shear stress due to the shear force at that point is going to be 0. Now that we have calculated all of the relevant parameters, we can go ahead and calculate the stresses due to each of the internal forces. And here is my calculation for the shear stress due to the shear force Vy, and here is the calculation for the stress due to the torque T, and here is the calculation for the stress due to the bending moment M. We know the shear force produces a shear stress, and the direction of the shear stress is going to be in the y direction, vertically up, is going to be in the same direction as the shear force Vy. The magnitude of the shear stress is going to be 0 for point D because there's no capital Q for that point. The magnitude of the shear stress at point E is given by this equation, VQ over IT. And you can easily follow the details here. And I get a value of 1.696 megapascal for that. The stress due to the torque T is also a shear stress. Its direction is perpendicular to the radius at every point. So at point E, it's going to be vertically up, and at point D, it's going to be horizontally left. The magnitude only depends on the radius, and therefore the magnitude of the stress due to the torque is going to be the same at point E and point D. The magnitude is calculated using this equation, Tc over Jx, where T is the torque, C is the radius, and Jx is the polar moment of inertia. So once again, we have all the numbers up here, and we calculate a value of 25.5 megapascal for that. The bending stress is a normal stress in the x direction. In other words, it's a stress on the x-plane in the x direction. So I'm calling that a sigma xx. The magnitude is 0 at point E because this is the neutral axis. The magnitude at point D is calculated using this equation, my over I. M is this, y for point D is the radius of the circle, which is 0.05 meters, and I is calculated over here, so 4.911 times 10 to the minus 6 meter to the power of 4. So that leads to a value of 203.6 megapascal, and from the direction of the bending moment, you could see since point D is above the neutral axis, that point is going to be subjected to a compressive stress. Now we combine the stresses, paying attention to the type and the directions. We see that the normal stress is produced only by the bending moment, and the stress is 0 here, and the stress at this point is 203.6 megapascal compressive, and that's the only source for that. The shear stresses are produced by two different sources, the shear force Vy and the torque Tx. And this first picture here depicts the shear stress caused by the shear force Vy. We have the maximum value over here, and that value is 1.696 megapascal. The direction is vertically up, in other words, in the positive y direction. And the shear stress is 0 at this point. The shear stress produced by the torque is perpendicular to the radius at every point. So at this point, it is vertically up, and at this point, it is horizontally to the left. The magnitude is 25.5 megapascal. So now we can see at point D, the shear stress is produced only by the torque Tx, and it is going to the left. At point E, however, they are produced by both the shear force Vy and the torque Tx. So they become additive. You add the two to get the net shear force in that direction. Alright, so with that understanding, let's take one point at a time and mark the stresses on a differential element drawn around the point. So here are the components of the stresses at point D. We have a compressive normal stress in the x direction of 203.6 megapascal. The only shear stress at point D is in the x-plane acting in the z direction, right? So that'll be this plane right there and going in the z direction. All right, so the magnitude is 25.5 megapascal. There is no normal stress at point E. The magnitude of the net shear stress due to the shear force V and the torque T is 27.2 megapascal. This is the shear stress acting on the x-plane in the y direction. So that'll be tau xy. That's it. So those are the components of the stresses acting at point D and point E.